Hey, welcome back, folks. Friction is one of those things that pops up in a huge variety of problems that we'll do in physics and situations we'll consider. It arises basically from the idea that stuff is bumpy. Every surface has some amount of bumpiness to it, even something that feels very, very, very smooth. Think about how it's constructed. It's made out of atoms, which have roughly a spherical shape to them. So if you imagine trying to stack or organize a bunch of like play pit balls to make a perfectly smooth surface, you can't do it. You've got little bumps and you've got divots because of the shape of the things that you're building with there. Or go to the supermarket and look at the fruit. The apples, the oranges, these circular fruits, there's no uniform surface to it. It's all bumpy. So you get two bumpy surfaces together and we have some interlocking of bumps and grooves. Friction is how we describe that on a bigger scale. We can't see necessarily the bumps and grooves catching on each other as two surfaces slide past one another. So we just describe the effect as being friction. So we have a couple different varieties, and we'll look into that more with this video. And then you'll see just a wide variety of problems going forward that will have friction playing some role. So if I have a box on the floor here and I'm pushing the box over, let's give it some movement, some velocity over to the right. When we zoom in and we look at those little bumps and grooves that make up the surface of each, we can see that there will be some times where a bump on the purple surface lines up with a groove on the red surface, or vice versa. There's some interlocking going on there. And so as our box is moving over to the right here, every once in a while, the right edge of a bump on the red will hit the left edge of a groove on the purple. We have some little collision between bumps and grooves there. And so from there, we're stuck. And so how do we get unstuck? Well, basically there's two options. The box can lift up a little bit from the floor, so disengage from those groups a little bit. Or it can break off a bump or a groove from either one of those, break off a bump, I guess, from either one of those surfaces. And both of those things happen, actually. So when you push something across the floor, we can hear it sliding across the floor. That sound that we're hearing is the sound of little vibrations in those two surfaces as the box and the floor are kind of bumping across each other, bouncing past one another there. If you think about rubbing two things together, we also know that we can make things smoother by doing that. Say, rubbing sandpaper on a piece of wood. You can make it smoother because you're using that sandpaper to knock off bumps from the surface of the wood. And so that idea, that way of thinking of it, gives us a good way to start approaching the direction of friction. And also the idea that there are two different types of friction. So first off, direction. The direction of friction, people will say opposes motion, but that can be misleading in certain situations. Like if we have both our objects moving already, friction opposing motion, well, relative to what? And so if we have like a big block sliding across the floor and there's a small block on top of the big block, opposing motion, which direction is that? Is that trying to make them both go the same speed, or is it trying to make everything stop, or which direction opposes motion? So instead, we're going to say that the direction for friction is such that friction will always oppose sliding. Friction opposes sliding of two surfaces past each other. So whatever the motion of the object as a whole, friction is trying to get these two surfaces to stop bumping into each other, to stop having collisions between bumps and grooves. And we give it a little more credit there. It doesn't really have that intention, I want to stop the bumps and grooves from hitting each other. No, it's an effect of the collision. So when you collide with something, you get slowed down by it. You may slow down, and the object that you hit may slow down. You kind of come to a common state of motion there. And the same thing happens with, with very, very small particles here. Air resistance functions much the same way. We'll talk about that a little bit later on. So friction tries to get these two surfaces, if they're sliding past each other, tries to keep them from sliding past each other. Now, what if they're not sliding past each other? What's different there? Well, not a whole lot. We still have this force that if I push this box one direction or the other, we still have bumps and grooves that are kind of interlocked a bit. But since we've let these objects, these surfaces come to rest, they sort of nestle into each other a little bit more thoroughly. We give these things time to settle into one another a bit. And so the bumps on one surface find the grooves in the other. And sometimes the surfaces will actually change their shape to match up with the other shape a little bit. A really extreme version of this would be like two Lego blocks interacting. And so if we have two Lego blocks that are stuck together and we try and slide one of those past each other, when they're locked, we're not going to be able to do that unless we apply enough force, well, to break off the little nubs from one Lego block. And that's the same thing that's happening here. If I want to start my purple object moving this direction, I can't do it unless I break off this little nub and this little nub, maybe this little nub here. We have little pieces that have to break off. Or there's this big hill. We really have to move this bump upward to get it to clear this little nub on the green piece there. So it's this tighter interaction. You could also kind of weave your fingers together or weave your knuckles together and try and slide your hands past one another to get that same experience. So they're really, now we've settled in, and it's hard to get out of that. A macroscopic example, another macroscopic example would be if you're driving your car through an area with speed bumps. And so you can go over the speed bumps, and if you have some speed to begin with, they might slow you down a little bit, and you should certainly slow down before you get to them. But the speed bumps themselves might slow you down a little bit, so you have to hit the gas to speed back up. But it's a fairly minimal effect. It's enough to make us want to slow down. But if you imagine stopping your car so that the front wheels are just barely touching the speed bump, and then trying to go again, you might be surprised at how much you have to rev your engine just to get over that little speed bump. We didn't have to give it a significant amount of gas to get over the bump when we had some forward motion that would help to carry us over that bump. But if we stop right at the base of it, that's a much bigger deal. Sometimes you find that in parking lots too. You just park in a spot that a lot of people have parked in before. So there's a little bit of a groove, and you go to back out, and you almost wonder, like, Josh, did I leave the parking brake on or something here? Because it feels really hard to get out of that little groove from the previous tires there. So it's all about having time and having inclination or ability to really settle in, to make these two shapes line up in a matching sort of way. And so when we have to break big chunks off like that, or really go up big hills to get past the surface past one another, that's harder than just having them bumping along across each other, where we don't really have the time or the forces required to get these two surfaces to settle in with one another. And so we divide friction up into a couple of different categories, a couple different types of friction. We'll have static friction and kinetic friction. There are actually other types as well. Rolling friction, fluid friction is a term people use sometimes when there's a lubricated interaction between two surfaces. But we'll just focus on sliding friction and kinetic friction. Static friction, I think, because it's sliding, but static friction and kinetic friction. Static friction opposes the start of two surfaces sliding past each other. So this is for two surfaces that are not currently sliding past each other, but there are forces present trying to make them start sliding past each other. Kinetic friction, that's for surfaces that are already sliding past each other. They're bumping along past each other, but they don't, since they're moving, they're bumping along, they don't settle in, the bumps and grooves of the surfaces don't settle in with each other quite as much. And so what we find is that static friction can be a much stronger force for surfaces than kinetic friction can be. You might have noticed this if you ever try to move furniture around your house. Give a couch a push, and you really have to give it some oomph to get it going. But once it's moving across your couch, it's not quite as difficult to keep it going as it was to start it going. So you don't have to push quite as hard once it's already moving. Now, part of that is whether you're accelerating it or keeping it at a constant velocity, but part of that is related to static friction being a bigger force than kinetic friction. Or at least it can be. Here's the weird thing about static friction. It has a range of possible values. If I have my purple box here at rest on the red surface, and there's no forces trying to push the box to the left or to the right, it would be a mistake to say that right now there's a frictional force going this direction. That is wrong. So if there's no forces left or right, and I say, yeah, there's friction going to the left, that now becomes my only force in the horizontal direction. And if that's the only force, I can't have a balanced force situation, so my box would have to be accelerating to the left. But I know it's not, it's just sitting there. So if it's just sitting there, and there are no forces to the left or to the right trying to make it move, there's actually no frictional force at this point. And then if I apply some force here, maybe it's a rope tied to the box, so we'll say that's a tension force going that direction, and we'll just make it a little force to start with. Then my box, I'll say I'm not pulling hard enough to get it started moving, so it's a heavy box, I pull on it, but it doesn't go anywhere. Well, there must be friction now in this case to keep it still. That friction must be the same size as the tension force and act in the opposite direction. Now, if I pull a little bit harder on the rope, but my frictional force, or my box still doesn't start to move, then my frictional force must also be a little bit bigger. And if I pull a little harder on the rope and my box still doesn't move, then my frictional force must be a little bit bigger as well. Eventually, I pull hard enough, my tension force is big enough that the box starts to move. And at that point, those grooves, they aren't engaging with the bumps fully here. And so we jump to that kinetic friction state. And with kinetic friction, regardless of speed, we have a single value for kinetic friction. So the force to the left from this frictional force will have some single value. And we also find that the value of that kinetic friction is less than the maximum value for the static friction. Now, how much less varies a bit, but we find that kinetic friction force, so I'll put a K in here for kinetic friction, that kinetic friction force has a smaller value than the maximum value for the static friction force, but static friction has a range of possible values based on the other forces. Now, how do we deal with that mathematically? We find that the frictional force depends both on how rough or smooth these surfaces are and how much force there is trying to squeeze those two forces together. And it turns out that whatever forces are responsible for squeezing those two surfaces together, the total of all those forces, those squeezing forces, is going to be equal to the normal force that's trying to keep them from squeezing into one another. And we know that that's the case because the surfaces don't meld and become one. They don't pass through one another, so we must have some balance there. And so our normal forces then, in normal situations anyway, in most situations anyway, the normal force will be equal to maybe gravity. If it's just gravity down and normal force upward, the normal force would be equal to gravity. Or maybe we have some extra downward force or some extra upward force on our surface, and so we might have to incorporate that into our normal force. So if we're pushing our box down into the floor, in addition to gravity pulling downward on it, then we've got a bigger normal force, and we'll have more friction as a result. Normal force doesn't have to oppose gravity. If you push an object against the wall, we could have a normal force pointing out away from the wall, and that'd have to be equal to the size force that we're pushing it against the wall with. But in any of those cases, we find that as our normal force grows, so does our frictional force. Now, how do we deal with the range of possible values for static friction? That's right here. Static friction, we say, has a maximum value, but we don't give it a set value here. Now, mu k, and mu s, mu just represents the ratio between the kinetic friction force and the normal force for mu k, and between the maximum static friction force and the normal force for mu s. We call it the coefficient of friction. It's just the coefficient that we add to this normal force to get us to the frictional force. Or we could write it as the ratio of frictional force to normal force. The coefficient of friction really is just a way to express how well those two surfaces, the bumps and grooves on those two surfaces, how well they interact with each other. So it's a measurement of how rough those surfaces are. Bigger numbers go with rougher surfaces that will have more interaction. And so with these equations then, we have to keep in mind that when we do a calculation for an object that has friction acting on it, we need to be mindful of whether that object is still on a surface, at rest on a surface, or whether it's moving across a surface. And sometimes we won't know. Sometimes we won't be sure whether it's at rest on the surface or moving past one. So we might have to look at all the forces that are trying to move it across the surface and compare to, the maximum possible value for the static friction. And if the maximum value for friction is bigger than the total of those forces trying to make it move, then the object doesn't move. Our friction can cover it. It doesn't make it doesn't cause motion there. We could also have a case where we have an object moving with some amount of forces acting on it. We maybe had to give it more force to start, like that couch example. So we give it some amount of force to get it going, and then something in the problem would tell us this thing is for sure sliding across the surface, though we may actually not be providing enough force that we could start it from rest. That frictional force might be bigger than the force that we're applying to it. So if we just apply that force to it when it's at rest, it just stays right there. But if we give it a little bigger force to get it moving and then apply that smaller force after that, that might be a big enough force to not allow our object to come to rest over time. We might be able to balance out the smaller kinetic friction force. So there's a lot to consider with friction. Which case we're dealing with, whether it's static friction or kinetic friction, as well as when we get into static friction, whether we're at this maximum value for static friction or whether we're in the less than that range, whether we're not quite maxing that out yet. So a lot that we think about with friction, but mainly, the friction stuff is just going to be part of larger problems for the most part. It fits in as a force in the x or the y direction when we do a Newton's second law calculation. So watch for friction calculations, probably not all by themselves, but as part of larger problems. Thanks very much, folks. If you learned something from this, by all means, subscribe, leave a comment, give me a like, whatever you like to do with videos. Thanks very much, folks. Have a good one.